And yeah, so it's all about deep RL, stable baselines, if you're interested. And his main focus is on learning controllers directly on real robots. And this, I think he will talk about very much in his talk, and also improving the reproducibility of RL.
Thank you. Thank you for the introduction. So yeah, today I would like to talk about recent advances in reinforcement learning for continuous control. And if you want to follow along, all the slides are available on my website already. Just so that everyone is on the same page, although you had some talk yesterday, let's just go back quickly to RL 101. So this is Bert, it's a quadruped robot, and here it has an arm on top of it. And in RL, we usually talk about different things. We tend to talk about the agent, which is here what we care about, so the robot. And the agent can interact with its environment through actions. So it could, for instance, walk, it could move its arm. And the environment in return will give some feedback to the robot. So it will give the current state of the robot. So actually on real robot, it will be more like observation of the state. You don't have access to the true state. And some measure of how good is the robot doing right now. So a reward. And through interaction, the idea is that you can learn a controller that can improve over time only by interacting with the environment. If you ever attended an RL talk, you will have heard about sample efficiency. And today I would like to talk about two ways of improving RL algorithms. One way is to improve sample efficiency. So it means that for reaching the same performance, you want to use as less steps as possible, as less interaction with the environment as possible. So in that case here, you can see that algorithm B in green is more sample efficient than algorithm A. So it takes less steps in the environment to reach the same performance. And here we are really talking about sample efficiency. We are not talking about improving performance, although the two might be linked. And there's different cases where you would be interested in improving this sample efficiency is if you are using real robots. So when it's very costly to do any interaction with the environment, or in your case, if you have a particle accelerator, you don't want to spend too many hours interacting with it. And also in simulation, sometimes you have very slow simulation, like with on chemistry simulation. And it's also good, even if you don't have real world interaction, to be as sample efficient as possible. And another way to improve algorithm is to have faster algorithm, so to improve on speed. So here, the x-axis is now time, so it's how much time do you take to train your controller. And again, you reach the same performance, but here algorithm D, again in green, is faster than algorithm C. And this, you want to have it in different cases. Like if you have a very fast simulator, usually running on GPU, you don't really care about samples anymore. You just care about how much time do you take to train your agent. And also, if you tend to use actually sample efficient algorithm, they tend to be quite slow. So if you manage to make it faster, it's always more interesting to be able to run it real time on the robot. And the outline of today will be first for me to quickly get you up to speed in RL into state-of-the-art approaches, because all the recent advances in algorithm that I will present are on top of the soft actor critic algorithm. Then I will also present some advances in software that are also linked into making things faster and into enabling the use of sample efficient algorithm. And I will finish some advances in simulator that also changed the RL world. By the way, for anyone there or online, I will also stop after the first part. So if there's any question, I can already answer them and you don't have to wait until the end. Another disclaimer is here, I will mostly talk about off-policy algorithms, so algorithms that tend to be more sample efficient, because that's the one I'm usually using in robotics for training on real robot directly on the hardware. There's also a category of algorithm like the PPO algorithm. I will quickly talk about it at the end. So the goal for me is to bring you from the DeepQ network algorithm to SSE in 10 minutes. But let's go back to the basic. So the DeepQ network, or DQN for short, was introduced in 2013, 2014 by DeepMind, and it was quite of a revolution because the same algorithm managed to solve a lot of different Atari games directly by interacting with those Atari games from pixels. So it received the game state, so the pixel as input, and by interacting with its environment, it will learn to solve the different games. And all the components that were used in this algorithm are actually still in use in most RL algorithms. So it was also very interesting to see putting all the components together and making it work at a bigger scale. And it started out also a lot of interest in reinforcement learning. So let's go back to the basic. In RL, what do we want? We want to maximize the sum of discounted rewards. So we want to reach the best performance. It translates, if you write quickly some math, into maximizing the sum of discounted reward given a current policy pi. So that's the controller that you are trying to learn, that you are trying to optimize. And the discount factor is here for two reasons. So the discount factor, you can see it as a trade-off between maximizing short-term reward, which you are more sure to get, versus optimizing for long-term reward. Also, if you have an infinite horizon task, usually a control task, it's good for the math that you have a discount factor, otherwise you would have an infinite sum. And there's many different ways of solving this problem, of maximizing the sum of reward. And one of the way is actually to learn something on the side, which is called an action value function, or you will usually see it in the RL literature as a Q value. And this action value function tells you how good is it to take an action A in the state S. If you write the definition, so for a given controller, for a given policy pi, if you take the action S, the action A in the state S, what do you expect to get? So it's very similar to the RL objective I just presented. The main difference being that you start in a specific state and you take a specific action. And if you manage to estimate this value, then the problem is solved because you can just take the argmax of this Q value, and then you will definitely take the best action that you can in every state. As you might think of, there will be some problem with that later. And the last thing I would like to talk about for the Q value is we tend to use in practice, another equation for learning, which is a recurrent equation. Basically, it tells you that how good is it to take this action A in the state S is how good am I doing immediately? So you're just looking at the immediate reward, and then you're using the Q value itself to look in the future. And this is actually how you can estimate the Q value, because then you can have a regression target here where you use the previous iteration of your Q value as a target for estimating. And the DeepQ network came with different components that are now reused in every off-policy algorithm. So the first component is a Q network. So to approximate the Q value, it uses a neural network. And to stabilize the regression, because if you look at the last equation here, the Q value here is a moving target. As soon as you update the Q value, this target is updated, and that can be a problem. So instead of directly optimizing for this Q target, it uses a frozen copy of itself that is slowly following it, which is called the target network and also used by many RL algorithms. Then the next component is a replay buffer. So basically, it's just a big first in, first out queue with a lot of experience, a lot of data from the interaction with the environment. And this allows to reuse data more often, so to be more sample efficient. And this also allows to have more independence between the data, because if you're just using the stream of data in RL, then you will have samples which are very correlated to another. And the last component it was using was to have some trade-off between exploring, so between testing new actions that are potentially better, and using the best actions so far. The DQN training look like that, and it's the same for almost every RL algorithm. It alternates between collecting experience, so using the current policy, using the current controller, and collecting some data in the environment and filling the replay buffer. And then every n steps, it stops and updates the network using gradient descent by sampling data from the replay buffer. And once the policy is updated, you can go back to collecting new experience with the updated policy. And over time, you hope that it will get better and better until you actually use all your budget. So far I've presented DQN, and DQN is working only for discrete actions. If you recall, for DQN, what we can do is we can just list all the possible actions that you can take in the particular state and take the best one. So just taking the argmax of your Q value. The problem is if you're in a continuous action problem, you will have an infinite amount of action. So it's very hard to take the argmax of this. So one way to counteract this problem, you could do some sampling, or you actually can learn another network that will be, its job will be just to maximize the Q value, so to approximate the maximum function. And this other network, we will call it pi of phi, so because it will also be your policy. If it tells you what is the optimum action to take in a specific state, this is the controller that you want. This is what you need. And basically, the idea of deterministic, deep deterministic policy gradient, or DDPG, is really to approximate the maximum using another network. So the phi is some weight of your neural network, and the same for theta here. And you try to learn something that maximizes your Q value. And because Q of theta and pi of phi are both differentiable, the way you train everything is by just using gradient descent. So you will compute what is the current Q value estimated for the action taken by your policy. And then you will backpropagate the gradient to the policy such that this guy is maximized. One problem with estimating the Q value is usually we have overestimation problem and overestimation bias. What does that mean? That means that if your observed data looks like that, so it's all the black dots here, you will be very good at estimating the Q value around the data that you have. But outside this region, you will have some extrapolation error. And if your approximation overestimates, because you are trying to take the max of the Q value, you will try to take action that you have never seen, which can be quite dangerous, and which will also lose some time during training. So one idea to counteract this overestimation bias is, instead of having only one approximation of your Q value, is to have an ensemble of functions. So you will learn two approximations, Q1 and Q2, and you will take the minimum of those two Q values. And that way you can reduce the overestimation bias, and it actually in practice improves performance a lot. And this is the idea behind twin delay DDPG, which improve a lot on DDPG, and by using this twin network. So by using two networks and taking the mean of those two to reduce the overestimation. And soft actor critics, so you heard of it yesterday if you attended some talk, was introduced in 2018 and is still state of the art right now for continuous action. And is basically combining everything as just presenting. So you can see that as a DQN for the main component, so using a Q value approximation, using a replay buffer, using target networks. It's using TD3 twin networks to reduce overestimation bias. And it optimizes an objective that is slightly different. So it optimizes what's called the maximum entropy reinforcement learning objective. And this objective is slightly different from the RL objective. It encourages exploration, so it encourages the policy to be as random as possible while still solving the task. If you write the objective, you still have your sum of discounted reward here. So you try still to solve the task given the policy pi, but you have some entropy bonus here with some factor alpha, and the factor alpha is a trade-off between exploration and exploitation. And this is the main idea behind SSE. It's combining everything and also having the trade-off between exploring and exploitation directly in the objective. So for now, and as an example of what does that mean to have an entropy bonus, is if you are in continuous action, you tend to parameterize your policy using the Gaussian distribution. So, and having this entropy bonus will prevent your Gaussian distribution, at least the variance of it, to collapse too early. Right now, we'll stop a little bit because there was a lot of information in a very little amount of time. So if you have any question, I will be very happy to answer right now. Otherwise, I will continue into the advances of algorithms. Also online, you can write question. I'm looking. All clear? Or everyone sleeping? I don't know. Okay. So I just presented the soft actor-critic algorithm, and now recently in the last 4 or 5 years, there have been some advancements for improving sample efficiency and for improving training speed. And the first improvement I want to talk about deals with something particular. So usually in real-world reinforcement learning, your environment is stochastic. What does that mean? That means that if you take the same action A in the same state S, you don't always get the same outcome. So let's say here I've got my cute quadruped Bert trying to jump the cliff. And because we don't have perfect information about the robot, perfect information about the environment, when it tries to jump, maybe there's some wind we didn't measure properly. By doing the same action, sometimes it will succeed, sometimes it will fail, although it's exactly the same action. And it's a problem because in reinforcement learning, we tend to always look at the expected performance, so what happens on average. But here we have really, we are taking a risk, and this is hard to model with the classic reinforcement learning. So this is the idea behind distributional RL, is instead of just estimated what is the expected performance, you try to estimate the real distribution of performance, the real distribution of return. So what does that mean? Here I'm plotting the expected performance, so the Q value, in a given state, taking a given action. And I'm trying to model a bit what happens in the previous environment. So you will have a very small probability of getting a very high performance. So it means probably taking a risk. And it will have a high probability of failing, so getting a low return. So despite taking the same action in the same state, you get a distribution of outcome. And the problem with classic RL is that you only model the expected performance. So you will be a bit between those two modes. And this will be very hard to actually optimize because you will have always some error when you sample one or the other. So the idea behind truncated quantile critic is to model this using quantile regression. So to model the different quantile of this distribution, and to overcome the overestimation error is you drop the highest quantile. So so in a way that you try to underestimate a bit your Q value. In terms of results, it's very similar to SSE, but on some harder environments, it tends to be actually better. It costs a little bit of training time. Then on some environment which are harder, like here you have some you have to overcome some obstacles. SSE will be very hard to train or needs very tuned hyperparameter, where TQC will handle it pretty nicely. So TQC improve on sample efficiency and sometimes also improve on performance. Another way to improve sample efficiency, to learn faster with less interaction, with less sample, is to have a higher replay ratio. So the idea is very simple, is you have a replay buffer, so you have a buffer with a lot of interaction with the environment, and you might be thinking, well, we could reuse those samples more often from the replay buffer, so we learn more from it. The problem is if you just do that naively, it just doesn't work. You can try to scale it, so to sample from it very often, but you will end up with different problems. You will end up with some overfitting problems, some overestimation and extrapolation errors. And it's actually still an open problem to understand what is actually happening and how to counteract that. So I've listed the different papers if you are interested in looking more into that. One way to solve this problem and to enable scaling the replay buffer is to have some ensembling. So with the red Q algorithm, you have an explicit ensemble. So it uses 10 different Q value estimator and is taking the minimum of those. Or you can also have an implicit ensemble, which is the draw Q algorithm. It's using dropout for having some implicit ensemble plus some regularization like layer norm. In practice, this is how the standard SSE neural network look like. So it's very shallow if you do deep learning. It's usually two linear fully connected layers with some ReLU activation. And it has a replay ratio of 1. What does that mean? For every interaction with the environment, it is doing only one gradient step. What we want is probably have a replay ratio much greater than 1. So sampling from the replay buffer more often and reusing the data that is collected from the environment more often. What the DrawQ algorithm does, it adds some dropout layers for ensembling and some layer norm layer to avoid any gradient spike during optimization. And the other big difference is now it's sampling 20 times more the replay buffer than SSE. So it's slower, but it's also much more sample efficient. A small note also, it is optimizing the Q value estimation. So it is trying to make the Q value estimation converge and is only optimizing the policies, so the actor, the controller, every 20 iteration. And that's what called the policy delay. So the replay ratio is usually equal to this delay. So you train the Q value more often in a way that it converges first, and then you can train the actor network that is trying to maximize this Q value afterward. In terms of results, actually, it improved quite a lot in terms of sample efficiency, depending on the algorithm, on the environment, of course. Here it's a simple Mojoko environment with, it's called half cheetah, basically a sausage that is jumping. And it can be from 2 times to 4 times more sample efficient. So you really gain in terms of interaction with the environment at the cost of more training time. But as a roboticist, it's also very interesting because now it enables learning directly on the real robot. And this is what I did now 2 years ago, where I'm trying to learn directly on the real robot from scratch. And only in 10 minutes, it will manage to learn to move forward. So it's really learning from scratch. So at the beginning, it does nothing interesting. And after a while, after 4 minutes, it will do its first step. And then it will quickly learn to move forward. As a baseline, I did the same experiment 5 years ago, and it took from 5 hours to 8 hours with the SSE or TQC algorithm. So there was a huge improvement from 5 hours to now down to 10 minutes. And then it will plateau. By the way, all the algorithms I'm presenting today are actually implemented and available in the JAX variants of the Stable Baseline 3 algorithm. So, and the link is below. It's called SBX for short. Yeah, and that's what happened. After 10 minutes, it learns to happily walk forward from scratch. So another idea to improve sample efficiency is to have a bigger network. This is not a new idea. If you follow deep learning, people have been trying that from the beginning. The thing is, in RL, if you again try to do it naively, it just doesn't work. Try to have a deeper network, try to have a bigger network, it just doesn't work out of the box. So you need some specific architecture to make it work. And only recently with big regularized and I forgot the BRO algorithm and the Simba algorithm, people finally managed to have also bigger network. So as a reminder, this is the SSE default neural network with 2 layers. And for instance, what the Simba algorithm does, And what is quite interesting, it's just replacing the network architecture. It's not changing at all the algorithm, but by just changing the network architecture, you can get a performance boost. And basically, it's first normalizing the observation, which is also quite classic, and then using a residual network, the exact architectures, they benchmark different architecture to find the one that work best for reinforcement learning. That is also using layer normalization. And by only changing the network, so you lose a bit in terms of training time because it's bigger, but you can also improve on performance and on sample efficiency. One interesting thing with everything I'm presenting, so the last three improvements, so having distributional RL, having higher replay ratio, or having a bigger network, those improvements can be combined. They are not orthogonal. And actually, when you do combine them in practice, you tend to have even bigger gain. So in terms of results, again, by just changing the network architecture, on some environment, you can get a good boost in terms of sample efficiency. Here, I think you learn 4 times faster for the same task. Again, any question before I move forward about all the algorithm I just presented, or about still RL 102, and also online, if you have question, you can ask. A question, all clear? All right. Just move. Okay, so the next thing I want to talk about is some advances in software. And it's very linked to advances in algorithm, because some algorithm without advances in software would be impractical to use in the real world. And I will mostly talk about just-in-time compilation. So if you follow in the recent year, you might have heard of JAX. And I was actually curious about it. And then I tested it. And this is what happens. So on the x-axis, you have the time taken to train a particular agent. On the y-axis, you have the performance. And here I'm training the same algorithm on the same environment with the same hyperparameters. The only difference in one case, I'm using PyTorch, and in the other case, I'm using JAX. And by using just-in-time compilation, and also you need to rewrite everything in a functional way, you can get a huge performance boost. So for me, the performance boost here, I think, was from 2 hours to 10 minutes. So you can imagine that now you can iterate much faster. And on some other, yes, the speed up is between 5 times to 20 times faster. So it's a real game changer in terms of what you can do. And because you can do things much faster, you can also use algorithms which are normally too slow to run on real robots. And that's what I actually did. So in the video I shown the DrawQ algorithm, if I would not be using JAX, it would just not be possible to use it on the real robot. On the real robot, I was able to do 10 gradients updates at 30 Hz. So it was really, really fast. But luckily, if you use PyTorch, PyTorch is working on PyTorch compile. And if you want to learn more how to have a better boost with specific implementation, you can have a look at the LeanRL library. And those two, yeah, really makes things faster, enable you to iterate quicker, and allow you to have more sample efficient algorithm. So I presented some advances in algorithm on top of the SSC algorithm. I presented a quick advances in software that goes well with advances in algorithm. And I want to finish with simulators. So if you've been, again, around in the last 2-3 years, you might have heard of massively parallel simulation. So the idea here is, instead of simulating just one thing on the simulator, is to have 1,000 of robots in parallel. And because you have 1,000 of robots in parallel, you don't care at all about sample efficiency anymore. You just care about how fast can you train. And with the right hyperparameters, you can actually train in minutes instead of training much longer. And you can have a very diverse training. So you can have the robot trying out many different configurations at the same time in parallel. Of course, it has a cost of approximating some contact forces, approximating some other things to make it faster. But it's again also a real game changer. If you have been following the advances in quadrupeds or humanoids, a lot of people now are using those simulators. And I want to mention some of them. So you might have heard of MGX, which is the JAX equivalent of Mujoko. There's obviously Isaac Sim and also Genesis more recently that also has some fluid simulation included. And if you read any of the papers about massive parallel simulation, they will tend to, all of them use the PPO algorithm for proximal policy optimization. This one is a bit more lightweight than SAC, but it tends to be faster in terms of gradient update. And it will, the recipe for PPO working on those massively parallel environments is first to have a very large mini batch size. So the classic, at least the default one, tend to be 64, and here it would use a much larger mini batch size. So using a lot of transition in parallel, so from 100 times more, 10 times more to 100 times more. It also uses a bigger network. And to adapt the learning rates, it's using a Kullback-Leiber divergence adaptive learning rate schedule. So what does it mean? It is measuring the KL divergence between the old policy, so the previous controller and the updated controller. And depending on the distance between those two, it will adapt the learning rate. The way it works is, you define a target KL divergence. And if the jump between the previous policy and the new policy is too big, you will reduce the learning rate. But if the difference between the previous policy and the new policy is too small, then you will increase the learning rate. And this tends to also give the best result because you don't need to care at all about tuning the learning rate. You just give this schedule and give the two bounds between which you want to optimize. Another thing that you need to be aware of is most of those environments have unbounded action space. And that can be a huge problem if you want to use an algorithm that is not PPO. PPO is fine because it's using behind the scene an unbounded Gaussian distribution with a standard deviation initialized around 1. So even if the action space is infinite, it will only explore a little portion of it. But some other algorithm like SAC uses a different distribution, and that makes it impractical. If you try to switch naively from PPO to another algorithm on the simulator, it will just not work. Actually, if you want to read more about that, I did a full blog post about getting SAC to work with those parallel simulator. And one of the main things was to have proper action space, so to restrict the limits in a way that really represent what you want to control and not have infinite action space. And to get other algorithms to work on those environments, you can also do hyperparameter optimization. So you can really optimize those algorithms for speed. Again, that's what I did with SAC because everyone was using PPO. And if you just quickly try to make SAC work with those massive parallel simulator, you will get the curve in red or orange, in orange. So basically it will learn, it can still learn quickly, but it won't reach the same performance as PPO, and it will still take 12 minutes. So you might think 12 minutes is not much, but if PPO is taking 3 minutes or 4 minutes, usually you don't want to use that. If you use hyperparameter optimization and tune it for speed, you can actually get similar results. So you can obtain good performance quickly by choosing the right set of hyperparameters. And in addition to that, actually SAC here uses less samples. And the main, I would say, for me, the main idea behind using SAC in simulation with this massive parallel simulator is to later, you can deploy your train controller and continue training. Because with PPO, it will be prohibitive to actually continue training because it's very sample inefficient. So if you use the same algorithm in simulation and in the real world, then you can pre-train in simulation and continue fine-tuning on the real robot. So to conclude, I presented different ways to make things more sample efficient. by having more advanced algorithm like TQC that using that optimize distribution of that is estimating the distribution of outcomes. You can also have a higher replay ratio with, for instance, draw queue, or you can have also a bigger neural network and combine all of them. Together with those advances, there's all the just-in-time compilation that can make things much faster. So from 2 times to 10 times, 20 times faster. And for that, you can have a look at JAX and Torch Compile. And I finished with a faster simulator running on GPU, where here you don't care about sample lessing anymore. You just care about how fast do you train. So with IsaacSim or MGX. So that was it for me. And if you have any question now, that's the moment.
Hi, sorry, I tried to raise my hand, but I guess I couldn't.
Good.
Can you hear me?
Yes, we do.
Yeah, sorry. Actually, if you can come back to slide 21. Actually, I have a naive curiosity and question that maybe I missed at some point. That you say that here it's working I mean, you are doing parallel simulation here. Means that each robot is learned in parallel, but independent on each other. Just in the space, they are dependent on each other. Is correct?
I'm not sure to understand the question, but maybe to explain a bit more what's happening is here, what is in parallel is a data collection. So you have 1,000 robots in parallel that is collecting data using the same policy, the same controller. And they don't actually, if you look at the simulation, they don't interact with each other. The contact between each of them is deactivated, so they can pass through each other. But what you really parallelize is the data collection.
Yes, then this data is independently collected for each parallel processing. Why I'm saying this, I mean, you put in this into simulation, but when you do these robots that you will have sensors, and then in the same space they share. I mean, they share the same space means that in some way they can share all the same data. And when you do this parallel processing or parallel simulation, and then this is just the encoding way you did, just for curiosity, if you added those parts, it means that the learning process will be independently also dependent at the same time. I mean, in the simulator, did you put also the same space for all the data that collected and then how to say, optimize to each other? Just I'm trying to understand. Sorry, I'm not so expert. Just trying to understand this point. Sorry for nice question.
I'm not sure to understand the question, and maybe you, because we don't also hear so well.
You can also send him an email in case
Yes,
for further clarification.
Okay. Thank you very much.
Yeah, sorry, many. You were first by.
Hi, thank you for the talk. It was really really interesting. I don't know too much about reinforcement learning, but nice to learn. So apologies if this is incorrect, but a lot of reinforcement learning starts from scratch, or is there a way to feed certain actions or certain behaviors as a starting point for a lot of these models to learn from on top of?
Yeah, actually, that's a lot about my PhD thesis, which is all about how do you integrate prior knowledge for your robot, because learning from scratch every time is prohibitive and definitely not the best thing on the real robot, because you will break it, and this is very costly. So there's many different ways of providing the robot with some knowledge so that it doesn't start from scratch. One way is to design your experiments in a way that you already have some knowledge included. That's why actually I use, instead of, for instance, commanding the joint position, I can directly command in Cartesian space. So I'm using some inverse kinematic to command in Cartesian space. So a lot of redundancy doesn't have to be relearned. Or in your case, if you want to provide like an example, you can, for instance, fill the replay buffer with some behavior that you know that might be interesting to start from. Or you can even use what's called residual reinforcement learning. So you can have a base policy that already does most of the work, and then you learn a delta on top of it. So that's, for instance, 3 ways of not starting from scratch and improving the result, and especially improving safety in my case.
Well, thanks. I was also wondering if, maybe this is again misunderstanding, but for instance, in DeepSeek, you can see the process of learning. I'm wondering if there's a similar visualization of the process, the thought process of reinforcement learning.
What would you expect, for instance, for a local motion controller? I'm curious.
Sure.
Okay.
Okay. Anyways, yeah. Thank you.
Okay.
Hello, thank you for this very nice talk. I also have the same caveats as the other question. I'm not in this area, but I wanted to ask about the role of this replay buffer, because I don't think I very well understood that. Is that like the whole history, or do you sort of delete things from the buffer at some point? And then, or do you like penalize the early stages of the buffer? Because I think, isn't the bits at the first going to the buffer, they're under like a different policy, aren't they? Because you update the policy as you go along. So that's what I was wondering about.
Yeah, so the replay buffer is there for different reasons, but to answer quickly your question, yes, you tend to delete all experience, although in practice, the replay buffer tend to be quite big, like 1 million interaction. And if you make it too small, it will actually tend to overfit the latest data and then forget about, you have some catastrophic forgetting. And then it will try action that it knew it was bad, but because it's no longer in the replay buffer, it can have got erased. So yeah, that's one reason. Yes, it's from different policy. It's from older version of itself. But actually, that's why we use a specific category of algorithm that can handle that. So they can handle data which is from different policy. In practice, it's from policies that are still not too far from it. Otherwise, it will not be so useful. You actually have a full field now in reinforcement learning, which is called offline reinforcement learning, which is all about having a fixed data set from any policy, from any data collection that you can do, and try to learn as much as possible without interacting with the environment. So, and it's all about being conservative with respect to the data. And the replay buffer, yeah, has different role. One of the main role is to be able to reuse sample and to have also more independent samples. Like when you do supervised learning, you have a data set and you randomly sample from your data set. In reinforcement learning, if you didn't have the replay buffer, you will need to use the stream of data. And the stream of data, because you have this loop of taking the action, getting the new state, it will be highly correlated between every sample. And this is violating quite some assumption when you do some gradient descent. So that's also one way of improving things. I hope I answered most of your question.
Thanks. Any more questions? I think
there would be one
first.
online afterward.
I have one online, if possible.
Yeah, let's just go. Yeah.
Yeah, thank you for this super nice presentation. I was wondering, for the case of non-stationary control problems, so where the environment is changing and maybe all data might not be as useful, I was wondering about your take on algorithm selection, because would it be more sensible in that case to go on policy, or do you still tackle these problems with off-policy approaches and with everything that you mentioned before in the talk?
Yeah, actually, for me, the choice between on policy and off policy really is a matter of, do you care about training speed or do you care about sample efficiency? And also, how much can you parallelize your environment? It's true that if you keep the replay buffer too large, you will sample things that are very useless for your new problem. But you can also reduce the replay buffer and it will still work, although it might be slower to update. Again, you have some hyperparameters that you can tune to move more quickly towards the new dynamics. And for instance, would be to change the Polyak coefficient, so to change how fast is your target network tracking the new Q network. So yeah, but for me, the main difference is what really matters for you. Does sample efficiency matter, or does training speed and parallelization matter?
It will be more on the lines of just adapting to the new dynamics as soon as you see them or they occur in an environment. So yeah, it will be more in that sense. Yeah.
And maybe to add something, also PPO is not fully on policy because it reuses the data multiple times and then it discards it. And it has also, I mean, it has this trust region mechanism, which prevents it from having too big jumps between two updates. So even if it's supposedly on policy, you might still have some lag using PPO in that case.
Yeah. Thank you very much.
Yeah, okay. Thank you very much for the nice talk. I was wondering, maybe I got it wrong, but on the PPO slide, you said it's very efficient for large, small mini batches, basically. Is there a difference in the efficiency for batch sizes for SAC and PPO?
Let's say it's more here. It's what tuned hyperparameter work for those type of environments. So it has been shown that the bigger the batch size, the faster it can learn, because the policy gradient will be less noisy also. With SSE, unfortunately, if you just try to scale the batch size, it won't work as nicely as with PPO. I'm actually trying to work on that, and if you have a solution for that, I would be very happy, because this would be also very interesting when you can have 1,000 of environment in parallel, because you could really increase the batch size more. So it's more a hyperparameter that tend to work and that has been shown to work with massively parallel simulator more than anything.
Okay, thanks. Yeah, nice talk. Thank you. I'm wondering, can you say a bit of details on the reward function you use? So specifically with robots, I once came across this funny idea of using actually like some human-based rewards, where you would actually judge whether or not the robot performed a proper looking action, like for example, a flip forward and not a somersault, something like that.
Yeah, actually, so where is it? I have actually a video showing you how to train a robot just from human reward. I just need to see where it is. It should be not too far. But it's in another one. I will. Yeah, here you got this one. So for the learning directly on the real robot, the problem I've shown is actually a very, very simple reward function. It's using just optimizing for the forward velocity. And that was it. My whole point was to see how simple can the reward function be for learning on the robot. But you can also, and this is what I did more recently. So you have the robot, and you're trying to train it as quickly as possible by just giving this human feedback of good robot, bad robot. Here, I'm using black box optimization, so you can see that as episodic reinforcement learning. And this will actually be tested normally soon with an astronaut from the ISS in some. And the nice thing with that, if you parameterize your policy the right way, here I'm using some open loop oscillator behind the scene, it can really quickly learn again to move forward, or also to turn, or to do anything that you would like and quickly. And this really allows you, for instance, to model things that are hard to code. Like if you want some styling reward, this is really hard to code here. You can really see, yes, you're moving forward, but I don't really like it. And the nice thing is this interface can also be used by anyone. I also use on people which are not familiar with robots, and it worked also again in 5-10 minutes. So that was also very interesting to have a very simple reward scheme, good robot, bad robot, and be able to learn directly on the real robot in minutes. The main difference with RL here is that the policy was it was restricted to locomotion, and it was using black box optimization, so episodic reinforcement learning. And this is what happened when you replay the same policy. It was also learning a population of solutions. So even though you train to move forward, maybe you have a policy that turn left, and you can save it for later.
It's very nice. Thank you.
So which black box optimizer was that? Just for curiosity.
So I use different one. Now I'm using the CMIS algorithm, so using evolution strategy, mostly because I know how it works, and then I can tune a bit the parameters for what I need. But any other algorithm might work. It's just that this one was working well. I knew how it works, and it was also escaping some local minima in simulation.
Okay, any other questions or comments?
Question online, maybe? No question.
Maybe I have just one again out of curiosity. So when you actually tuned SEC to compete with PPO for the massive parallel simulations, what was the key hyperparameter, or was it really several? No?
It's several hyperparameters actually. I'm writing a blog post about it, so it's not yet ready, but mainly to tell you were the key ones. One was the one defining the replay ratio. So how often do you want to sample your replay buffer compared to how many data that you have? And here in that case, because we don't care about samples, you have a replay ratio which is below 1. And actually the replay ratio I used was like 0.03, so like just 3% of all the data I'm collecting. Another one is the policy delay. So it's how often do you update your actor network, your policy network compared to the Q network, because this will save also some gradient steps. And then tuning some others, but that's I would say the main ones so far, and having also bigger network. I think we answered that question already. I think we answered that question. Please tell me if I didn't, but I think I did.
Okay, last chance. Any more questions? Now, if not, then let's thank Antonin again. I think it was really great.